Today, we're tracing the architectural shift that paved the way for most modern AI, building on our previous discussions of the transformer in cases like hashtag TCM 063001 and hashtag TCM 123005.
We know transformers use self-attention, but what was the core problem it was designed to solve? Why did it fundamentally change the game so much?
Before 2017, the status quo for tasks like language translation were these complex architectures. The authors note, the dominant sequence transduction models are based on complex recurrent or convolutional neural networks.
And recurrent means processing things one step after another, right? Like reading a sentence word by word, which can be slow.
Exactly. Even these earlier models recognized the power of context, and often the best performing models also connect the encoder and decoder through an attention mechanism.
So attention existed, but it was an add-on, not the main event.
That's the key insight of this paper. They boldly declared, we propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
Completely getting rid of recurrence? That feels like a huge gamble. How do you process a sequence without processing it sequentially?
Think of it like cooking. Recurrent models are like stirring a pot, adding ingredients one by one. The transformer is like putting everything in a massive oven at once.
So instead of one ingredient affecting the next, everything influences everything else simultaneously? That's the parallelization?
This analogy works well for understanding the parallel processing aspect. However, unlike a real oven where ingredients might combine randomly, the transformer still allows each ingredient, word, to selectively interact and inform every other ingredient in a structured way, which is where the analogy breaks somewhat.
Precisely. The paper immediately highlights this benefit. These models are more parallelable and requiring significantly less time to train. This unlocked scaling.
Less training time meant we could build much larger models faster, making them more practical.
And it wasn't just faster, it was better. It achieves 28.4 BLE on the WMT 2014 English to German translation task, improving over the existing best results.
So faster and better? That's a clear win. It's not just a theoretical improvement, it performs.
The transformer proved attention could do it all. Now, let's peel back the layers and understand how this revolutionary architecture works, starting with the high-level view.
From a black box to how it processes input into output, I'm ready to see inside.
This excellent illustrated guide from J. Elamar begins by grounding us. The transformer was proposed in the paper, Attention is All You Need. It visualizes the black box we just discussed.
So we feed it a sentence, and it gives us another sentence back, like in machine translation. Simple on the outside.
When we look inside, we see an encoding component, a decoding component, and connections between them. This is standard for sequence-to-sequence models.
The encoder processes the input, and the decoder generates the output. What's inside those?
The guide shows that the encoding component is a stack of encoders, and the decoder is a similar stack. Each encoder performs a specific step of processing.
So it's not just one big encoder, but layers of them, each refining the understanding of the input.
But wait, if we're processing everything in parallel and ditching recurrence, how does the transformer know the order of words? Dog bites man and man bites dog have the same words but very different meanings.
Right. Traditional models relied on sequence. Without it, how is order preserved?
That's where the original paper introduces positional encoding. Before any attention layers, a unique numerical pattern, a specific kind of positional encoding, is added to each word's initial embedding based on its absolute or relative position in the sentence. This allows the model to understand sequence without sequential processing.
So it's a clever trick to inject spatial information into the otherwise order-agnostic parallel computation. The model sees position through these added signals, effectively restoring the sense of order.
Each encoder has two main sublayers. First, the encoder's inputs first flow through a self-attention layer. This is where the magic of contextual understanding happens.
Self-attention. We've mentioned it before. What does it actually allow the model to do?
Consider the sentence, "The animal didn't cross the street because it was too tired." Humans know what "it" refers to, but for a machine, what does "it" in this sentence refer to?
That's a classic ambiguity problem. Without context, it could be the street or the animal.
Self-attention solves this. When the model is processing the word "it," self-attention allows it to associate "it" with animal. It creates a dynamic link between relevant words.
So it's like the model asks, who cares about this word? And then gives more weight to the important ones. To be clear, the model isn't asking consciously, it's performing mathematical comparisons that result in weights. But the effect is to emphasize relevant words.
Unlike an RNN's hidden state, which accumulates information sequentially, self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing.
It's not just remembering previous words, it's actively determining their relevance to the current word simultaneously. That's a huge shift in how context is built.
After self-attention, the second sublayer is a simple feed-forward network. Crucially, the exact same feed-forward network is independently applied to each position.
Independently? So once self-attention has established the context, the rest of the processing for each word can happen in parallel again.
This independence in the feed-forward layer, combined with parallel self-attention computation, is why the transformer is so efficient. Now, let's unpack how self-attention actually works with vectors.
Okay, the how of self-attention. I want to see the query, key, and value vectors you mentioned.
The first step in self-attention is to create three vectors from each of the encoder's input vectors for each word. These are called the query, key, and value vectors.
So from one word's embedding, we get three new vectors. What are they for?
These Q, K, V vectors are generated by multiplying the embedding by three matrices that we trained during the training process. These matrices learn how to project our word into these three distinct roles. These matrices learn how to project our word into these three distinct roles.
These QKV vectors are generated by multiplying the embedding by three matrices that we trained during the training process. These matrices learn how to project our word into these three distinct roles. It's not hard-coded.
Think of it like searching for videos. What are the query, key, and value vectors? Your search query is the query. The video titles and descriptions are keys. The video content itself is the value.
So the query searches through the keys to find relevant content, which are the values. That makes sense for connecting words.
This analogy beautifully captures the roles of Q, K, and V in finding and retrieving relevant information. But unlike a search engine that returns a list, the transformer takes all the relevant video content, values, and blends them together based on their relevance scores to form a new, richer representation, rather than just picking one. The next step is calculating a score for each word's relevance. We do this by taking the dot product of the query vector with the key vector of the respective word.
Dot product measures similarity. So if my query word is similar to another word's key, they get a high score.
If we're processing word 1, its query, Q1, is compared to every key in the sentence. The second score would be the dot product of Q1 and K2, comparing word 1's query to word 2's key. So every word queries every other word, including itself, to see how relevant they are. That's a lot of parallel computations.
So every word queries every other word, including itself, to see how relevant they are. That's a lot of parallel computations.
After computing all scores, we divide the scores by 8, specifically the square root of the dimension of the key vectors, which is 64 in the original paper, so 8. This scaling helps stabilize gradients during training. Then we pass the result through a softmax operation. This normalizes them into probabilities that sum to 1.
This means each score now represents how much attention or weight that word should get. Softmax makes it a distribution.
This is crucial. This softmax score determines how much each word will be expressed at this position. It's a learned weighting, allowing flexible contextual blending.
So instead of just grabbing a single word, it's taking a blend of all words weighted by their relevance.
Next, we multiply each value vector by the softmax score. The intuition is to amplify relevant values and diminish irrelevant ones.
The value holds the actual information of the word, so we're selectively taking information from other words based on their relevance.
Finally, we sum up the weighted value vectors. This resulting vector is the output of the self-attention layer for our current word, enriched with context from the entire sentence.
So each word's output is a unique blend of all other words' information, where the blending ratio is determined by the learned attention scores. That's a very rich representation.
What we've described is a single attention head. The transformer actually uses multi-headed attention. Instead of just one set of Q, K, and V matrices, it uses multiple sets, each learning to attend to different aspects of the input. For example, one head might focus on grammatical relationships, another on semantic ones.
So it's like looking at the sentence through several different lenses simultaneously, each capturing a different kind of relevance. That makes the contextual understanding much richer.
Exactly. These separate attention results are then concatenated and linearly transformed. The illustrated transformer notes that this design choice helps make the computation of multi-headed attention mostly constant relative to processing a larger single vector while enhancing the model's ability to capture diverse relationships. This detailed mechanism for self-attention, bolstered by positional encodings and multi-head attention, is at the core of the transformer's power. But no technology is without its trade-offs.
So what are the practical considerations and limits of this revolutionary architecture?
While the transformer brought immense benefits, it's important to note its limitations. One major challenge is that the computational cost of vanilla self-attention scales as quadratic complexity with the length of the input sequence. Processing very long documents can become prohibitively expensive, a point the original paper addresses when comparing to recurrent layers.
So even with parallelization, there's a practical limit to how long a text it can efficiently handle in its original form. And what about the sheer scale of training?
Indeed, while individual inference is faster, training large transformer models, especially foundational models like BERT, requires massive datasets and enormous computational resources, which can be a barrier to entry for many. Despite these challenges, the transformer's encoder proved to be an incredibly powerful building block. This led to models like BERT that pushed language understanding to new heights.
How did an encoder-only transformer take language understanding so much further?
While the original transformer was proposed for machine translation, its encoder-decoder structure proved incredibly versatile. But what if you only needed the powerful contextual understanding of the encoder?
Like for understanding language, not necessarily translating it. Is that where models like BERT come in?
Exactly. BERT, or bidirectional encoder representations from transformers, takes the transformer's encoder, makes it deep, and trains it on massive amounts of text. Crucially, it's bidirectional because its self-attention allows every word to consider all other words in the sentence simultaneously, both before and after it, when forming its representation.
So unlike previous models that might only look backward or combine separate forward and backward passes, BERT gets the full picture from both directions at once, through all its layers. That's a true contextual understanding.
To achieve this deep bidirectional understanding, BERT was trained using two novel tasks. The first, masked language modeling, involved randomly hiding some words in a sentence and training BERT to predict them. This forces the model to learn deep contextual relationships.
Like a fill-in-the-blank game on a massive scale. It has to understand the grammar and meaning of the whole sentence to guess the missing word.
The second task was next sentence prediction. BERT was given pairs of sentences and had to predict if the second sentence logically followed the first. This helped it learn relationships between sentences, crucial for tasks like question answering.
So it didn't just learn about words, but about how sentences connect to form coherent text. This is why BERT became so foundational for so many NLP applications, far beyond machine translation.
Indeed, from a novel architecture relying solely on attention mechanisms to powerful models like BERT, the transformer truly transformed the landscape of AI.
And it continues to evolve. It's amazing how much one core idea can unleash.